All right, today we're doing a deep dive into a really specific and I think a fascinating technical problem. We're bridging the gap between two very different eras of video signals.
We are. We're looking at the NTI DVI-VGA converter.
And this thing, it really exists to solve one core problem, right? A major compatibility headache.
Exactly. You've got a modern computer, and it's outputting a DVI-D signal, which is purely digital, but you need to connect it to an older monitor, maybe a projector, that only speaks one language, analog VGA.
Okay, so let's really unpack that. The mission for us today is to get to the bottom of that technical challenge. How do you take a clean digital DVI-D signal and basically translate it into an old school analog graphic signal?
It's definitely not a simple pass-through. The whole function is translation. I mean, inside this converter, there has to be something called a DC, a digital to analog converter.
A DE, so
It physically changes that stream of digital data from the computer into, an analog voltage signal. That's the only way that legacy VGA display can even see an image.
And with any kind of translation, there are usually limits. There's a ceiling. So what's the handshake agreement here? What's the max output?
The sources are clear on this. The maximum supported resolution is 1280 by 1024.
1280 by 2024. Okay, so that gives us a very concrete boundary on the quality.
It does, and that boundary is directly tied to, well, what I think is the most interesting part of this whole thing, the bandwidth.
Okay.
The bandwidth for a DVI signal is listed as, get this, 1.6 gigahertz.
Wow, okay. That's huge.
It is. Now, compare that to the VGA bandwidth. It's only 165 megahertz.
Wait, hold on. Say that again. 1.6 gigahertz versus 165 megahertz.
Yeah.
It's a staggering difference. It's more than a tenfold drop. So what happens to all that extra data? I mean, are you just throwing away 90% of the signal?
That's the big question. It's not so much throwing it away as it is a very complex filtering and data reduction process. The converter has to manage this massive drop in data rate.
How does it do that?
Well, it focuses on what's absolutely necessary for that 1280 by 1024 image, things like color depth and the sync timing. It has to filter out all the extra high-frequency data from the digital stream that the analog VGA pipe, it just can't handle.
I see. So it's being selective. It's prioritizing the critical information for that specific lower resolution.
Precisely.
Okay, that makes a lot of sense. So now that we've got our heads around the technical side, what about the practicals? What do you get if you buy one of these?
Well, this is a very specialized piece of kit. The part number is just DVI-VGA. It's small, TAA compliant, and it comes with everything you need.
So you get the converter itself.
You do. And it comes with the DVI-D cable and even a little VGA gender changer, so you're covered for pretty much any connection scenario.
And this isn't some cheap adapter you'd grab at a checkout counter, is it?
No, not at all. Today's price is listed at $240.
$240. And that price really tells the story, doesn't it? It reflects that this is active digital to analog processing, not just, a cable with different pins on each end.
Absolutely. So when you boil it all down, what this device is doing is successfully forcing this massive high bandwidth digital stream into a much, much narrower analog pipe.
It's an impressive squeeze play, really, translating data on the fly to keep that legacy tech alive.
It is.
And that leads us to our final thought for you to mull over. We know this conversion process has to be lossy. It's shedding a huge amount of data to make that 1280 by 24 image work. So the question is, how does the hardware decide what to sacrifice? What gets the chop? Is it perfect color accuracy? Is the sharpness of the image, the anti-aliasing, what's being left on the cutting room floor to make that conversion possible?